morning students, welcome back in this lecture of the numerical analysis. In my previous lecture I was talking about the Regula Falsi method and secant method. Now in this lecture I will solve question based on these two methods. Then I will discuss about the fixed iteration method and Raphson method. So let us solve few questions based on this Regula Falsi and secant method. So perform 4 iteration of secant method and Regula Falsi method. For this equation x cube minus 5x plus 1 equal to 0 to get the root of this equation. So solution, let us assume fx equal to x cube minus 5x plus 1 equal to 0. So if you put x equal to 0, then you can see that this is your plus 1, and if you put x equal to 1, then this is your 1 plus 1 minus 5, so we have minus 3. So here we have positive sign and here we have negative. So therefore our root lies in the interval 0, 1. So let us assume x0 equal to 0 and x1 equal to 1. Now our first iteration is given by, so let us find out the root with the help of the Regula Falsi method. So our first iteration is given by x2 equal to x0 f of x1 minus x1 f of x0 divided by f of x1 minus f of x0. Your x0 is 0, so this term is 0. Your x1 is 1 and so this will be your f of x0, and your f of x0 is equal to 1 and our f of x1 is equal to minus 3. So your x0 is 0 and your x1 is equal to 1 and your f of x0 is equal to 1. So this is your minus 1 divided by f of x1. F of x1 is minus 3 minus f of x0, it is equal to minus 1. So we have 1 by 4, that is your 0.25. Now your x3. Now let us find out the value of this function at this x2, whether it is positive or negative. So we will use the calculator to find out the root of this equation. Now the value of this function for this x2 is equal to minus 0.2343. So therefore, which is your negative? Earlier our root was positive for x0. So our root will lie between x0 and x2. Therefore root lies in the interval x0, x2. So therefore your x3 will be x0 into f of x2 minus x2 f of x0 divided by f of x2 minus f of x0, and this is equal to, now your x0 is 0, so this term is 0, and this is your minus x2, so your minus x2, your x2 is, and your f of x0 is 1, so we have here x2 is 0.25 and your f of x0 is 1, so divided by this f of x2, which is your minus 0.2343 minus f of x0, which is your 1. So this is equal to 0.20254. So the value of this x3 is equal to this one. Now the value of the function at this x3 is equal to 0.20254. At this value, our value of the function is equal to minus 0.00. Then we have 4, 3, 9. Now the value of function at this x3 is equal to this one. Now your x4, and again you can see that this is your negative. So this is negative, and at x0, again at x2 we have the value of the function as negative, and at x1 we have the value of the function negative, but at x0 we have the value of the function as positive. Therefore, our root lies in the interval x0 comma this x3. So your x4 will be equal to x0 f of x3 minus x3 f of x0 divided by this f of x3 minus f of x0. Your x0 is 0, so this is equal to minus x3. Your x3 is equal to 0.20254. Okay, let us solve directly. So this is equal to, your f of x0 is 1, so this is equal to minus 0.20254 divided by your f of x3 is equal to minus 0.00439 minus your f of x0, which is your 1. So this is equal to 0.201654. Now at this f of x4, the value of the function is equal to, so the value of the function at this point is equal to 0.000, then we have 698. So this is your value of the function. Again, this is your negative. Therefore, our root will lie in the interval x0 comma x4. Your x5 will be equal to x0 f of x4 minus x4 f of x0 divided by this f of x4 minus f of x0, and it is equal to minus your x4 is 0.201654 divided by this f of x4 and this is equal to 0.201639. Okay, again let us check the value of the function at this point. So it is equal to, the value of the function at this x5 is equal to 0.000, then we have 50, then 3296. Now again you can see that the value of the function at this point is positive. As we have to perform 4 iterations, this was your first iteration, this is your second iteration, then we have third iteration, now this is your fourth iteration. So at the fourth iteration, the value of the function x is this, equal to, the value of the function, the value of the x is equal to 0.201639, and at this point the value of the function is near to 0 in comparison to this x4. As the value of the function near x5 at x5 is near to 0, so our root will be equal to 0.201639, and you can see that this root x4 and x5 are correct up to decimal 4 places. So therefore our root is equal to 0.201639. So this is your root of this problem. Now let us use the second method to find the root of this particular equation. So with the help of second method, now in the second method we will use this formula xk plus 1 equal to xk f of xk minus 1, or let's write it as xk minus 1 f of xk minus xk then we will have f of xk minus 1 divided by, I just want to write this in a similar way to the regular falsi. So this is your f of xk divided by f of xk minus 1. K equal to 1, then your x2 will be equal to x naught, as our k is 1, so we have f of x1, our k is 1, so we have x1 f of x naught divided by f of x1 minus f of x naught. Your x naught was 0, so again this is your minus x1 into f of x naught, so this will be your 0.25. Now the value of the function at 0.25 was equal to minus 0.2343, and this was your negative. But we do not need any change of sign here, so put k equal to 2. Let k equal to 2. So your second iteration will be equal to x3. Put k equal to 2. So we have x1 f of x2 minus x2 f of x1 divided by f of x2 minus f of x1. Now your x1 is equal to 1, your x2 is this one, so this is equal to, so let us guess this value. Your x1 is equal to 1, so we have 1 into f of x2, so we have minus 0.2343, then we have minus x2 minus 0.25 multiplied by this f of x1. Your f of x1 was equal to minus 3. Now we will divide this one by f of x2, which is your minus 0.2343 minus f of x1. Your f of x1 was equal to minus 3, so we have plus 3, and this is equal to 0.18646. Now the value of the function at this x3 is equal to, now the value of the function, our function was x cube minus 5x minus 1 plus 1. Now the value of the function at this 0.18646 is equal to 0.0741. So your x4, put k equal to 3. So your x4 will be equal to, if k is 3, then we have x2 f of x3 minus x3 f of x2 divided by f of x3 minus f of x2, and this is equal to, your x3 is 0.18646 multiplied by f of x3. Your x2 is equal to 0.25 multiplied by f of x3, which is equal to 0.0741. Then we have minus sign x3, which is your 0.18646 multiplied by f of x2, which is your minus 0.2343. So this is divided by f of x3, which is your 0.0741 minus f of x2, so we have plus sign 0.2343, and this is equal to 0.201726. Again, let us find out the value of the function at this x4. So the value of the function at this x4 is equal to 0.-0.000421. Your put k equal to 4. So this was your first iteration, then we have the second iteration, now this is third. In the fourth iteration, our x5 is equal to, if we put k equal to 4, then this will be your x3 f of x4 minus x3 x4 divided by f of x4 minus f of x3. So this is equal to, now your x3 is equal to 0.18646. Then we have f of x4. Your f of x4 is equal to minus 0.000421, and then we have to subtract x4, which is your 0.201726 multiplied by f of x3, and this was divided by your f of x4, which is your minus 0.000421 minus f of x3, which is your 0.0741, and this is equal to 0.201639, and the value of the function at this x5 is equal to 0.201639 is equal to 0.000, then we have two more 0 and 329. Now you can see that as the value of the function at this x5 is near to 0, so our root in this case will be your 0.201639. So with the help of second method, we have this root. Again, with the help of this Regula Falsi method, our root was 0.201639, and these two roots are correct. So here we have solved this particular question. We have evaluated the root of this particular question in the interval 0, 1 with the help of both with the help of the both Regula Falsi and secant method. And Regula Falsi method, you can see that one end point of the enclosing interval is fixed. Initially, our root was between x0 and x1. Again, your root was in the interval x0, x2. Then our root was in the interval x0, x3. And then our root was in the interval x0, x4. So that means in our Regula Falsi method, one of the end point will always remain fixed, whereas in secant method it varies. Because I am telling this because it is very important when I will calculate the order of convergence of these two methods. Now let us solve one more question with the help of this Regula Falsi method. So solve or find the root of by Regula Falsi method. Here we have to find out the root of this equation by Regula Falsi method. So let fx equal to x log x base 10 minus 1.2 equal to 0. So if you put x equal to 1, then we have 0. Now if you put x equal to 1, then we have minus 1.2. Now if you put x equal to 2, then this is your again minus 0.5979. This is your negative, again we have negative. And if you put x equal to 2, x equal to 3, then we have the value of the function as 2.2313. So which is your positive. So you can see that our root of this particular equation lies between 2 and 3. So this implies that our root lies in the interval 2, 3. So let x0 equal to 2, then the value of the function at this x0 is equal to minus 0.5979, and if you assume x1 as 3, then the value of the function at this x1 is equal to 0.2313. Now our first iteration is given by x2 equal to our first iteration is equal to, now your x0 is 2, so we have 2 into f of x1, which is your 0.2313 minus x1, which is your 3, multiplied by f of x0, and that was your minus 0.5979, and this is divided by f of x1. Your f of x1 was 0.2313 minus f of x0, which is your 0.5979, and you can see that this is your 0.272, 2.721056. So this is your x2. Now let us find out the value of the function at this x2. So at this x2, the value of the function is equal to minus 0.01705, and again this is your negative. So our root will lie at x1. We have the value of the function positive. So therefore, root lies in the interval x1 comma x2. So therefore, your x3 will be x1 f of x2 minus x2 f of x1 divided by f of x2 minus f of x1, and this is equal to, now your x1 is 3 multiplied by this f of x2. Your f of x2 is this one, 0.01705. Then we have minus x2, 2.721056 multiplied by f of x1, which is your 0.2313, and this is divided by f of x2. F of x2 is minus 0.01705. Then we have minus f of x1, which is your 0.2313, and this is equal to 2.740206. So this is your x3, and now the value of the function at this x3 is equal to, now the value of the function at this x3 is equal to 0.003838, and again this is your negative. So our root will lie in the interval. At x3 we have negative, and at x1 we have positive. So our root will lie in the interval x1 comma x3. So your x4 will be f of x1 into f of x3. Then this one. So let us guess this root. Now x1, your x1 is equal to 3 multiplied by your f of x3, which is your 0.003838 minus x3, which is your 2.74020206 into f of x1. Your f of x1 was 0.2313, and this is divided by your f of x3, which is your minus 0.003838 minus f of x1, which is your 0.2313, and this is equal to 2.7444. 2.74, then we have 4446. So at this x4, so we have this x4. Now you can see that our root is correct up to decimal 2 places. Now let us perform one more step. At this x4, our root of the equation is equal to, the value of the function is equal to this is equal to 0.00003315, and now this is your positive. So this is your positive, therefore root lies in the interval. Now at this x4 we have positive, and x3, at x3 we have the value of the function as negative, so our root will lie in the interval x3, x4. Hence, our x5 is equal to x3 f of x4 minus x4 f of x3 divided by f of x4 minus f of x3, and this is equal to, now your x3 is equal to 2.740206 into f of x4, then we have 0.003315 into f of x3. So we have this x3 into f of x4, then minus x4, which is your 2.7444 into 6 into f of x3. Your f of x3 is minus 0.003838, and this is divided by f of x4 minus f of x3. So you can see that this is your 2.74248. Now again our root is correct up to decimal 2 places. So let us find out the value of the function at this x4, x5. The value of the function at this x5 is equal to is equal to 0.001600. Now you can see that the value of the function at this x5 is near to 0 as compared to this x4, so we can say that this is our better root as compared to this x4. Therefore our x is equal to 2.742481. Again we can have more number of steps, and in the coming number of steps we can have the root correct up to decimal 3 or 4 places. Now let us discuss the fixed iteration method. Now our next topic is fixed point iteration. Our next topic is fixed point iteration. So let f be a real value function which fix every point, then a point x belongs to R is said to be fixed point if f of x equal to x. Now this x belongs to R is said to be a fixed point if your f of x equal to x. Now consider the equation fx equal to 0. So here we will find out the root of this fx equal to 0. So this is equation number 1. Now the fixed point iteration approach to this function, this equation fx equal to 0, is that it is rewritten in the form of the equation. Now the fixed point iteration approach to this equation 1 is that it is rewritten, it is in the form of an equivalent relation x equal to phi of x. So the fixed point iteration approach to this equation 1 is that it is rewritten in the form of an equivalence relation, which is your x equal to f of phi of x. Here this phi of x is known as your iteration function. Problem of finding the root of equation 1 become finding the fixed point of this iteration function phi x. If we start, x naught is the initial approximation to this equation 1. If x naught is the initial approximation to 1, then the sequence of approximation is given by this equation. So the sequence of approximation is given by this equation, where our n is equal to 0, 1, 2, 3 and so on. So with the help of this equation we can have the remaining iteration. Now the convergence of this fixed point iteration depends on the suitable choice of this x naught and this iteration function. Now here we can choose this x naught by drawing the graph, and with the help of the graph of the function we can take this x naught. So here I am not going in the convergence. In my next lecture I will discuss about the convergence condition of this fixed point iteration. So now let us start the Newton-Raphson method, which is basically a fixed point iteration method. So our next method is Newton-Raphson method. Let xn be the approximation to nth approximation to the root to the 0, say a, of the function fx. So let xn be the nth approximation to the 0 a of this, say, equation fx equal to 0. Now in Newton-Raphson method we replace our function by a tangent at this iteration. So in this method we replace our tangent, our function f by the tangent at the approximation xn, and the point at which this tangent crosses x-axis gives you the next iteration. So the point at which your tangent crosses the x-axis gives the next iteration. So let us draw the graph. Say this is your function and say this is your exact root, which is your a. We have assumed that our 0 of the function is a. Now let us draw. Say this is your nth iteration. Say this is your xn. So at this point our value of the function will be f of xn. Now let us draw the tangent at this point. So this is your tangent. Now the point at which the tangent crosses the x-axis will give you the next iteration. So this at this point we will have the next iteration. So this is your xn plus 1. Now the equation of this line, the equation of this tangent at this point P is given by so the equation of tangent at this P is given by, say, this y minus f of x fxn equal to the derivative, that means the slope, into x minus xn. Now the point at which the tangent crosses the x-axis will give you the next iteration. So for the next iteration we have y equal to 0, that means at this point, and the value of x at this point will be equal to xn plus 1. So your xn plus 1, now this is your minus f of xn divided by f of f dash xn, and it is equal to xn plus 1 minus xn. So from here our xn plus 1 is given by xn minus f of xn divided by f dash xn. So where our n is from 0, 1, 2, 3 and so on. So with the help of this iteration method, with the help of this iteration formula, we can have the remaining iterations. Now iteration method is your fixed point iteration method with iteration function phi x equal to x minus f x divided by f dash x, and the sequence of approximation is given by this xn plus 1 equal to phi of xn, where our n is equal to 0, 1, 2 and so on. So with the help of the suitable initial approximation, we can find the remaining approximation with the help of this fixed point iteration method. So this is all about this lecture. Now in the next lecture I will solve question based on this Newton's Raphson method, and then I will discuss the rate of convergence or bisection method, Regula Falsi method, and then this Newton Raphson method. So thank you so much for joining this lecture.